The paper explores the evolution of current-carrying cosmic string networks, focusing on the Witten superconducting model. The CVOS model is used to describe the statistical properties of these networks, with 4 macroscopic variables: RMS velocity, energy density, charge, and 4 current amplitude. These variables are defined in terms of root mean square values of time-like and space-like currents. The paper discusses the leakage of charge and current through 2 mechanisms: loop production and charge leakage, which can be described phenomenologically by introducing leakage efficiencies A and B. The time evolution contributions for Y and K are derived, showing that the specific form of charge leakage efficiencies must be inferred from field-theoretic studies and future high-resolution numerical simulations of evolving random networks. The energy density of the noncurrent carrying network is insensitive to these losses, and the paper demonstrates how this leads to a restriction on the equation of motion for the characteristic length Lc. The Witten model introduces a critical current, which affects the network scaling behavior during the radiation era, and its implications are discussed in detail. The paper concludes with a discussion on the limitations, assumptions, and potential observational implications of the findings. This research paper presents a comprehensive analysis of the evolution of current-carrying cosmic strings in the context of a cosmological network. The authors consider the interplay between the string network's characteristic length, velocity, charge, and chirality, as well as the energy loss due to loop production. They introduce an improved parametrization for the loop production function, which simplifies the system of equations describing the network's evolution. The equations of motion for the characteristic length, velocity, charge, and chirality are derived, assuming a Witten model for the cosmic string equation of state. The paper also discusses the constraints on the state parameter K, which determines whether the string is in a magnetic or electric regime, and highlights the instability that occurs when the tension becomes negative. The paper concludes by emphasizing the need for fine-tuning to achieve a dynamically stable regime, and outlines the range of the parameter that ensures a valid equation of state. The authors investigate the dynamics of a current-carrying string network, focusing on the Witten model, which incorporates a nonlinear equation of state. They derive constraints on the 4 current amplitude value, leading to a critical current limit, KCR, which depends on the chirality and string energy density. The equation of state implies a maximum chirality, KCR tilde operator O, 1, eta, where eta is a parameter related to the mass difference between the current carriers and the Higgs field. In the relevant regime, eta is defined as 1. The string network tends towards chiral conditions, with the largest deviation from chirality occurring when eta approximately equals 1, implying 0.33 is less than or equal to KSC is less than or equal to 0.86. This regime is of particular interest, as the backreaction on the underlying string is most significant, potentially leading to stable Vorton solutions. The authors also analyze the evolution of string currents, noting that the critical current limit will have a dramatic effect on the total current, Y. Although the actual RMS current, Y, can be boosted arbitrarily large in a Lorentz invariant frame, in an expanding background, the average total current is limited by the critical current, Y is less than or equal to KCR. To implement this limit phenomenologically, the authors introduce a nonlinear leakage coefficient, A, Y, which becomes E-dependent when YCR. This modification eliminates large current scaling regimes, unless the critical current itself is sufficiently large. Eta is defined as 1. The authors then examine the network evolution, first neglecting charge leakage and later incorporating it. In the no-leakage case, the network behavior is similar to the linear model, with the charge saturation value, Ymax, dependent on the initial chirality and scaling with the mass difference parameter, eta. After the radiation to matter transition, all solutions tend towards the currentless Nambu-Goto case. When charge leakage is included, the authors find that the critical current has a significant impact on network evolution, particularly for large critical currents. Eta is defined as 1. The nonlinear charge leakage term leads to a rapid escape of particles and energy from localized string regions, modifying the charge saturation value and eliminating large current scaling regimes. The authors conclude that the Witten model, despite its nonlinear equation of state, essentially coincides with the linear model for small chiralities, except for the critical current limit, which can be equally introduced in the linear model. This result highlights the significance of the critical current in describing the dynamics of current-carrying string networks. The study of cosmic string networks involves exploring the evolution of macroscopic quantities such as velocity, correlation length, current amplitude, and charge as functions of time. The underlying microscopic description is based on the equation of state derived within the framework of the Witten superconducting cosmic string field theory. This theory introduces several phenomenological parameters, including charge leakage A+, skew parameter G+, and bias parameters A and G, which should be calibrated from high-resolution field theory network simulations. The results show that the string network evolution is insensitive to the exact functional form of the charge leakage function, provided there exists a critical current above which the leakage becomes overwhelming. The network evolution with non-vanishing G+ leads to a similar behavior as in the case with G+ equals 0, due to a degeneracy between G+ and A+ parameters in the scaling solution. The study also investigates the impact of bias parameters A and G on the string network evolution. It is found that when A and G are non-negligible, the string network deviates from chirality and the evolution becomes distinct from the linear approximation. The deviation is estimated to be of order 1, whereas the number of dimensions. This implies that the bias parameters have a negligible effect on the network evolution when is large enough. The authors explore all possible cases for the relevant parameters and find that when charge leakage and skew parameter are negligible, the string network recovers the linear solution regardless of the value of the bias. The same result holds when charge losses are non-negligible, but bias parameters are vanishingly small. Finally, when all parameters have non-negligible values, the general solution exhibits distinct behavior from the linear approximation. The study highlights the importance of considering the microscopic details of cosmic string networks and their impact on macroscopic evolution. The results demonstrate the need for further research in this area, particularly high-resolution field theory network simulations to calibrate the phenomenological parameters. The analysis explores the evolution of superconducting string networks with equations of state beyond the linear case, specifically the Witten model. The study reveals that, for most physically realistic cases, the network behavior can be approximated by a linear equation of state on a macroscopic scale. This conclusion is significant, as it implies that the CVOS model offers a useful quantitative tool for exploring observational constraints on superconducting cosmic string networks. The research highlights that scenarios with a large current, frozen, network in the radiation era may have distinct observational implications compared to simpler Nambu-Goto networks. However, the evolution of charges and currents on the network depends on their equation of state and initial conditions, making it challenging to realize such scenarios. The authors find that, when the mass of the current carrier becomes much smaller than the string-forming Higgs field, the network approaches one of two possible scaling solutions, charged or Nambu-Goto, with different scaling values. The choice of solution depends on the network's initial conditions. A more detailed exploration of the limit where the critical current has a comparable energy to the underlying string is left for future work. This regime is particularly interesting, as it allows for significant backreaction and Witten formation. The study demonstrates that the CVOS model provides a useful framework for understanding the evolution of superconducting string networks. The authors conclude that the model offers a valuable tool for exploring the observational constraints on these networks, which will be the subject of a forthcoming analysis. The paper also provides an extensive review of previous research on superconducting cosmic strings, including their formation, evolution, and observational implications. The authors acknowledge the contributions of various researchers in the field, citing numerous studies that have shaped our understanding of these complex objects.